And let's not forget to share the slides. Okay. Looks good. So. Good. Everybody ready? Yeah? Max, you too? Okay, Max. So yeah, I was already, when planning this lecture on this day, I was already a bit like, okay, how smart is this? Given that there's a bridge day between, so, well. And then when rescheduling the assignment, like, okay, well, this is not going to make it better. So thank you very much for the hardcore fans of TADA that are here. Or, yeah, I don't know. I hope it's not that you really don't have a life, like, hey, what am I going to do? Let's just go to the lecture. I hope it's not that, but I hope there's some positive, positive drive to this. But good. So let me get rid of any distractions for myself. That makes everything better. Good. Okay, then let's get started. Welcome, everyone. Lecture number 9, if my counting is correct. We are actually today completely leaving causality behind for a change. I was rethinking this lecture, and in the end, it's remained very close to last year's because I think the setup is quite good. And what I was thinking of including more causality, but I think we had now the last 4 weeks, we had, well, enough of that, right? To now shift back a little bit. And well, there will be some under the hood in that, even if it's not right in your face. Good. So sequences, that's what it's at. Yeah, actually one remark. So yesterday I spent the entire day grading assignments because my schedule the last few weeks did not allow me to do this earlier. So I hope everybody received their comments. If not, get back to me because then something really slipped between the cracks or the mail server ate it. Let's see. The new assignment will be posted today or on Monday. It depends a little bit. I mean, I'm traveling this afternoon and I literally don't know how much time I have in between. So we have to see. But I think that after yesterday being a holiday in which, given the submission time, some of you did not really take the holiday, maybe starting on Monday is absolutely fine for everybody. I do hope so. Good. Okay, sequences. We continue our quest into analyzing non-IID data, because that's what we started to do last week, remember? There we were thinking about, okay, if we have multiple data sets, and they don't have exactly the same source distribution or the source mechanism. If we would throw everything onto one big heap, standard methods would fail. Now, this is exactly what you also kind of have in sequences, because rather than having one data set where every data point is generated completely independently in a sequence, well, it is of course possible, right? And if you have, there's no complete memoryless process, okay? But typically you would expect that the current time point, that data point is generated based on something in the past. And if we've also witnessed that, there is automatically no case of IID anymore. Points are not sampled independently. So, there's many forms of sequences. Typically we speak about time series when they are continuous valued. And we call about sequences if they are discrete valued, right? So text, for example, is a sequence, not a time series. And if you record, let's say, temperature over the day, that will become a time series. Although temperature, well, you might immediately say, okay, well, we're not going to measure this at infinite precision. So there we could also tokenize it, right, as we call it these days. And then actually you do have a sequence. So it is a bit of a, well, depending how you look at things type of topic. Nevertheless, today we will focus exclusively on sequences. So the question of the week or of the day is, how can we discover the key patterns from an event sequence? Okay, what is an event sequence? So if I summarize the entire lecture, we have some sequence with discrete tokens. Whoops, yeah, oh, I didn't know it could do that. Okay, I wanted to do my laser pointer, but somehow, there it is. Good. We have discrete tokens, A, B, D, C, and so on and so forth. And what we would like to find are, well, the key structures, right? And I'm going to use patterns because we already know what patterns are, or at least you could ask yourself, do we? Such that we can extract from this sequence ABC and DA, so ABC and DA, for example, here, another ABC, and so on and so forth. How can we get such knowledge, right? So how can we get an interpretable model from an event sequence? That is the overarching idea. So what is an event sequence? Well, we have an alphabet, I call this omega, set of possible tokens. Discrete events, could be words, could be alarms. So actually one of the motivating examples for me to even start looking into event sequences and mining patterns, mining interpretable models and the likes, was when I was working in Antwerp. Antwerp is one of the largest harbors in the world, and it also has a very large petrochemical industry. And petrochemical industry is, well, combustible. So it can explode relatively easily if things go wrong, right? So at one moment, we had a project together with some chemical plant in the harbor on site. And we were invited to sort of see part of the plant. And one of the things that was the most impressive to me was well, I forgot the name, but basically the room in which they have 3 people watching at a giant board with LEDs, most of them red, not all of them, and each LED is an alarm. Now, you would hope, in a way, that big chemical plant, right, can go boom, that this board was off all the time, right? I mean, there was no, not quite. There were like things going on all the time. And these 3 people, they had relatively short shifts, a bit like an air traffic controller, right? I mean, there's also people that have very short shifts because they need like to be super focused. And their job was to stare at the screen and to figure out if they should press the big red button that would shut down the plant. And, well, shutting down the plant really means like shutting it down completely, right? I mean, and it takes quite a while before then the problem has been found, before the plant can be restarted. So this is a very expensive measure, right? Shutting down the plant. You don't want to do this, not for fun. So their job was really to sort of track, like, wait a second, there's an overpressure in this valve, right? I mean, that's okay. If they just see, like, well, let's say a valve, you have multiple measure points, and just overpressure here, it moves to here, moves to here, moves to here, and you know that there's an exhaust valve or it will split, then it's fine. If it's like all of them red, bad, right? But it's not necessarily just the number of alarms going off. It's really like in which patterns and in which, well, particular sequential patterns, right? If first this one goes off and then that goes off, well, wait a second, that might mean that something is wrong. Now, such knowledge can partially be codified into rules beforehand, but typically, well, truth is stranger than fiction. So as a human, yes, you can come up with some rules, but they will not hold all the time. You will miss certain things like, yeah, of course, I should have included this. So the opposite approach of looking at the data and trying to figure out, are there any patterns in this data for which, well, the button was not pressed? And then presenting this to these experts, like, okay, well, why didn't you press, or should you have pressed or not? Then you can, of course, start to filter out from the screen, like, okay, well, this is a benign pattern, right? If this one follows after that one and just goes through the pipeline, this is benign. But if it deviates from that, then all of a sudden it becomes sort of a meta alarm. Okay, this is a pretty cool use case. At least I thought so, right? So hence alarms. Another use case that we looked into were train delays, where in the rail network, also in Belgium, we looked at well, let's make it every train station, just keep it simple. And we looked at, okay, is a train delayed? And particularly we're interested in, is there any sequential order in trains delaying other trains? So if it turns out that the train from Saarbrücken to Hamburg is typically 5 minutes late, or often, right? I mean, but that's just that, because it's not holding up any other train, then yeah, well, sorry, too bad, right? I mean, we can try to optimize this one train and the connections, but it's only a 5-minute delay times the number of passengers that you have. If, however, this train from Saarbrücken to Hamburg, by being 5 minutes late, blocks the platform in Hamburg for the train from here to there, and that one then is 5 minutes late, and that one blocks, and so on and so forth, then you have a whole pileup of delays because this one stupid train was 5 minutes late. Can we figure out these types of bottlenecks? Can we find out patterns between, well, delayed trains? This is in a very abstract manner. We can dive much more deeply into this topic, but again, a topic where you have an event sequence, right? Third example. I'm not going to go too much into process mining in today's lecture, but process mining is also a very interesting subfield that is strongly related to what we'll be discussing here. So before I continue, does anybody in the room or Max, you online, know what process mining is? No? Good. I also didn't know when I was in let's say, attending whatever the equivalent of TADA was that I took as a student. Process mining is the art and or the science of analyzing typically business process data. So I give a concrete example. Boris Wiegand, former PhD student of mine, he graduated last year. He is working actually still at Dillingerhütte. It's a steel factory in Dillingen, not so far away from here. But, and he was and is still working in the machine learning department, AI department, whatever they name it these days, where they're trying to use AI, ML to optimize their business processes. So, amongst others, so the key thing is that of course they know what the plant does, right? I mean, raw ore goes in, right? I mean, a nice flat, high quality steel comes out, right? I mean, sure, and there's a few steps in between that they also know roughly. Now, but there is a lot of small little tuning that is done by hand. And one of the key people at Dillingerhütte is called, I don't know his last name, his first name is Lothar. And Lothar was the one that they could ask, oh, we currently have this and this load, but we got this urgent order. Can we do it? What should we do? Like, yeah, okay, if you then route this one like that and such like this, and then actually rather than using the regular mill, you can use that one, and then everything is going to be fine. And if Lothar said no, then it was no, right? And that's, or it's like, oh my God, Lothar, I mean, the quality of the steel of this particular ore was not so good. Okay, well, then you should increase this. He was really like the data bank, right? But he was about to retire. Now, of course, you could have somebody shadow Lothar, right, and try to suck up as much knowledge, but they tried doing that, of course. The other thing you could do is like, well, we have a lot of data from the plant. Can we somehow learn a model for how things are actually going? And in a way that we can also look into this model, that we understand what is going, such that we can look into specific cases, what now happened where, and we can start to reason, right? That we also can find for specific instances where the quality of the steel or whatnot was not as good. Well, can we trace it back, right? Sort of anomaly detection or description in a way. Well, and so on and so forth, also for planning. Now, what are we actually doing? What is this type of data? This is data where at every step in the process, you log basically what you're doing. So we have this piece of ore, right? This goes into this machine. Then it does this. Then we do that, right? We push it through this rolling mill. And on this rolling mill, we were using that particular type of whatever setting, right? And so on and so forth. Now, we do this for every piece of ore, every piece of steel that we produce, or whatever. Let's say we work in an HR department. You also have all these process steps. Trying to extract this model, such as you can look into it and play with it, insanely valuable. So just to give an example there, Celonis, maybe you've heard of it, maybe not, is one of the few German unicorns. So this is a startup based, so it's came out of the group of Professor Wil van der Aalst. He's at Aachen. He's one of the big names in process mining, but it's actually based in Munich because that's where the students went. And well, this is essentially a company that goes to other companies. So give us your data, we'll do process, and we can tell you where you can optimize, where things go wrong or right. And well, valued above $1 billion. So, reasonable, right? So there is something to it. Process mining is effectively looking at event sequences. It's effectively trying to find patterns. If I see an A, then a B will happen. And a B could be, well, could take different forms or shapes. So just to show a little bit how extremely general this setting is, right? We're looking at the fundamentals here. So what does the data look like? The data could look like just one long sequence, right? This is a bit like, well, for example, the alarms data, right? Or it could be a collection of shorter sequences. This is what in the process mining setting. Could be either. And people have been looking at, well, at both. For us, for what we're going to be looking at, we don't care which form it takes. Most people do care. For us, it's just data is data. And well. Now, what is a pattern? A pattern is defined by a pattern language. And the standard pattern type that we'll be looking into for now, And some of you have done an assignment on sequences, so you know already a little bit what I'm talking about. But we can also do other things in addition. The key notion is that of a serial episode. And a serial episode is effectively a partial order. So here, the partial order says that A happens often before B, or B often happens after A, right? That's effectively. So a serial episode is kind of the equivalent of an item set, as we saw it a good number of lectures ago, right? But now there is an order all of a sudden. You could also read it as a subsequence, but we allow for gaps. It's not a strict subsequence. Strict subsequences you can also try to discover, but it's a bit less exciting. For example, here, this is AB as a strict subsequence. Here there is a gap in between, right? We still count it as an instance of AB. And, well, this is a regular one again. And here we could have, well, this is another one, this is another one, and so on and so forth. They don't have to be length 2. They can also be longer. You can also have a serial episode ABC or DBC. That would be an instance there, right? And then the traditional question would be, given a certain minimum support threshold, find all such serial episodes. However, how do we even count if something happens in a sequence? It's not so trivial. The main reason why I now went from tabular data last week, where I already showed we can break IIDness, to sequential data, and specifically event sequences rather than time series, which is a bit more common, is that sequences are the simplest complex data type in my book. Basically, all the things that are simple and straightforward and easy in tabular data become all of a sudden much harder in sequences. Perhaps not as hard immediately as in a graph, but mind you that if I take, well, a sequence, I can express it as a graph, right? I mean, A to B to C to D, directed graph. They map very nicely. They map very nicely. So the moment we can solve something in sequences, we already made a big stride forward compared to tables. So sequential pattern is a sequence itself. Doesn't have to be, but typically it is. And that means that to occur in the data, it has to be a subsequence. I already gave the example on the previous slide. For example, here, if this is the data sequence and this is the pattern, here we have an AB. Oh, whoops. So again, my laptop is doing weird things. No matter what I do here to fix it. Okay, you can give a formal definition, but intuitively, we just need to see the pattern in the same order in the data. Note that here, I do not parameterize in any which way the length of the data sequence in which I need to see, right, of which I can construct a subsequence that has the same length as the pattern, right? So in theory, for AB, it could be the first symbol of X and the very last symbol of X. And all the rest, right, so AB, right, and all the rest has been P, Q, R, and X, Y, Z, and whatnot, right? I mean, sure, that's still an occurrence. Okay, so whether that makes us happy, we don't know, right? But if you come from item set land, yeah, sure, it occurs, done, right? To already show that we now need to start to think about how much space in between do we want to allow, yes or no. There's more problems. Okay, well, this is not a problem. This is just an example. But, there we have the 3 examples. So now we can start to think about which of the subsequences in the data do we allow to be counted as truly supporting the pattern? Because there's going to be many of them, I mean, possibly exponentially many. So we can define the support of a pattern different ways. Note again that in item set land or tabular land is relatively easy, because there we just go like, is it a subset in a particular instance? And that's that, right? So we can, and also that means that within one transaction, which is an item set, well, another item set can either be a subset, yes or no, just once at most. But in the sequence, this is different, right? If I have a long sequence with AB, 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 and so on and so forth, do we see AB now many times, or do we see it one time? Do we adopt the item set type of occurrence, or do we really count? So the standard, the traditional one, is the per sequence support counting. So basically, per sequence in the database, x1 up to xn, we just simply see, do we see our pattern Z somewhere in the sequence? If so, then, well, the support goes up by 1. This is the simplest transfer. But if we're looking for AB and X1 is AB, 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 then sure, it makes sense to say AB occurs in this sequence, but it also feels like we're throwing away a lot of information, right? The equivalent, in a way, would be if we now have, let's say, not item set data, but I mean, we have a multi-set or something like this, or a bag, where, let's say, bread and butter, means somebody buys bread and butter, I mean, well, 3 of each. Okay, does this support the item set bread and butter? Yes. How often? Once, twice, thrice? More often? That's, I'm willing to go beyond, right, to explore wild ideas. It also supports the item set bread thrice, butter thrice. That also supports, but that only once, right? I mean, that's, So you already see that even there we can maneuver ourselves into a stranger spot than we were before. Okay, so but that is the standard per sequence support counting. In process mining, this often makes sense because, for example, a chunk of steel goes through some rolling mill, typically happens once in a sequence because afterwards we just have lots of other events happening, right? And we're really more explicitly interested in like, well, if I send this chunk of steel to that rolling mill and afterwards I do that with it, how often does this happen? And well, what does this do to the quality of the steel, right? Window-based support counting is where things get a bit more interesting. Window-based support counting is where we do wish to be able to pick up that if AB happens 3 times, that we get a support of 3, right? And 3 times in one long sequence. So what we do, we have a single sequence X, could also have multiple again, right? This generalizes. The support of a subsequent set is the number of windows. Basically, okay, so what can we do? A window, first formally, a window has a start and an end, right, in X. I write it like that, is a strict subsequence of X, right? Let's establish this, I mean, that, for now. We could, in theory, rather than really just having start and end, we could also just have an index set, just in some, well, full order, of course, right? I mean, that's, say it's this one, and that one, and that one, and that one, and what we could do, but let's say this makes things much more difficult, and I don't see the direct need for it. But if you are so inclined to fix the theory, okay, sure, we could do that. Let's keep it simple. We just have a start and an end, by which we define the sequence that we get like that. Okay, now what can we do? We again have the demo pattern AB. How often do we see AB? Well, we need to define now a window, right? I mean, we don't know the start and the end. I mean, suppose that I now set a window length of 2. Just as the example, right? Because the pattern is length 2. If I would set it to pattern length 1, then we have a trivial result 0, right? But with 2, let's see, right? I mean, just that carries then over from strict subsequences, obviously. That means that for every start, plus 2, right? That's basically the set of windows that we have. For each of those windows, we're going to look, do we see AB in there? If so, yay, otherwise, nay, and this is the way we count. So visually, look, there is AB. Up, there is not AB, also not AB. Whee! There we have AB again, right? I mean, I skipped all the rest, right? I mean, that's unless you really insist that next year I go no, 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 right? I mean, that I will do it to the next generation, right? So that's good. And there we also have, well, actually we have also an AB here, which somehow the animation skipped, but okay. But, in total, there's 4 strict ABs here. Very good. Okay. Now, yeah. Suppose that I would now not have a window length of 2, but of 3 or of 4, but longer than the strict length, right, of the cardinality of the pattern we're looking at. That means that all of a sudden I allow that it's A and then something else and then B, which is good. This is exactly what we want, right? We don't want to be too strict because maybe some alarm popped up in the middle and we don't want that to break everything, right? And that would be a bit too crude. Sure, we can do this, right? We can just sweep the window over it, right? I mean, intrinsically under the hood, nothing changes. But what we are counting and the meaning of it does change. Because, for example, if I now, let me see. No, I don't have the example there. Let's say we have a window of length 3. So, and we're looking at here, these 3, right? This is the window, AAB. Do we see AB in there? Yes. right? We do. Okay, now I move the window. Actually, so I could even ask, how often do we see AB in this window? But I'm not going to do that, right? I mean, that's. I now move this window just one to the right. Then we have ABC. Well, do we see AB in there? Yes. If I now would have a window of this length, right? So it's 6. Then I have AB. I move it. Well, I have AB. Again, next time I still have AB. I see ABs everywhere. I'm doubly counting in a way. If this is what you want, right? If you really want to have sort of like a sliding window histogrammy type of approach, right? But if you just want to know how often is there an AB in here, that's a very different question than how many windows include an AB. This is one of those subtle questions, right? Where you want the first one, then we can do this with windows. And many people then in a way stop thinking. I mean, this is not negatively meant because, well, this is a tool how to do this, but without thinking through, okay, what are the implications? My favorite question is, what could possibly go wrong, right? You already know this. Well, that. We will see many more ABs than. So, yeah, so formally, if this sequence supports a sequence, then anything that is a bit larger will also do and do multiple times. One of the fixes for this is a notion, which I like very much, is that of minimal windows. What we're doing there is that we say that, so we still have a window, let's say, of a certain maximum length, right? I mean, that's, but we see like, and we say, for example, here, because there's AB here, right? I mean, that's at the very end. Well, is there a sub-window of this window that still supports AB? Well, yes, because this one does, that one is minimum. I can shrink it all the way here. And as long as a window is not a minimal window, I'm not allowing it to count towards the support for the pattern I'm looking for. So I'm really trying to find the most compact occurrences. So in the AAB example, right, I see AB once if for a window of 3, because I can shrink it. If it would be AXB, okay, then I need window length 3. If it's A, P, Q, R, X, Y, Z, and so on and so forth, B, okay, then I need then the minimal window is very long. And note that we can now start to parameterize rather than a strict window length over which we're sweeping. It actually intuitively becomes more, what is the maximal length of a window that we would still say, okay, yes, that would be an occurrence of a pattern. So basically a maximum minimal window length, right? So for example here, AB, yep, here, this is not a minimal window, right? These are the minimal windows. So we have 5 in total. Now, how do we, with these notions, we can use either, or any or all of these support notions, right? I mean, that doesn't really matter. How can we now mine frequent serial episodes? So these are papers that were written in the mid-90s, early 2000s. And essentially, you take a standard algorithm that was developed for item sets that uses a monotone or anti-monotone support measure or interestingness measure. Well, our support is monotone. If we go from AB to ABC, well, the support will only go down, right, with these, if we parameterize it properly. So we can just take any of those and we have the sequential version of that. This is what people did. Can we also do this exactly the same trick with graphs? Yes, but no. Because here we have this notion of, well, subsequences, minimal windows kind of save the day, and we can compute those efficiently. With a graph, you have, well, isomorphisms. So if I give you a pattern, let's say a motif, right? I mean, so a subgraph and a big graph, and okay, well, where is it? Yeah, you basically, for every possible match, you need to figure out all possible. How many do you now count? Which ones? Graphs increase the heat quite a bit. But, good. Okay. Anyway, we're not going to go into these methods because just like with standard frequent item sets, they are essentially large-scale waste generators, right? So actually what we would like to find is a small set of the key building blocks. If there's the true pattern is ABCD, I just want ABCD, and I don't want ABC and BCD and so, unless those really have a significantly different frequency that like, oh, wait a second, yeah, A often doesn't happen, right? I mean, for, let's say, a particular type of ore, we don't first wash it or whatever we do to it, right? So we know that frequent pattern mining doesn't achieve this. We now go for pattern set mining for serial episodes. which means that we need to answer 3 specific questions. How do we score a pattern-based summary? You already have some intuition there. How do we describe a sequence given a pattern set? So I already give you a few of the serial episodes. How well, or how would you explain the data at hand? And then, well, last but not least, how do we then, if I don't give you these patterns to begin with, how can you find them yourself, optimizing both at the same time? So, first things first. We're going to be using MDL. So these are slides that I presented a good number of years ago. I adapted a bit for the lecture, of course. I'm not going to use them straight verbatim. But if you have like a wait a second, I already know this gist, yes, that there's a point to it, because well, I also want you to see the patterns, and then also like, wait a second, now I can connect the ideas. So does anybody have any questions about this slide? Does anybody know, or I mean, still wonder what MDL is? I hope not. Otherwise, I'm happy to explain, of course, right? The motto still remains, slight twist, optimal set of serial episodes is the one that describes the data most succinctly, that compresses the data best. What is our model going to be? Because that is always the key thing that you need to think of when you are using MDL. Not just MDL. I mean, I can already give a general comment there. Some of you did the assignment related to event sequences, where you had to compare the squeeze algorithm, the ISM for interesting sequence minor, if I'm not mistaken, and squish, 3 methods. ISM is a probabilistic based method. And some of you picked up like, hey, wait a second, this is actually very similar to MDL if we just hold it like this, or vice versa. And some of you were like, oh my God, this is so different. And yeah, well, that, depending on the rest of the report, this was still a pass or not. Because in the end, any such a method, no matter what footing it's based on, you need to have a definition of what is your model. In our case, what we have here on the left-hand side, again, sort of a code table, so we have this dictionary thing. We always include the singletons, such that no matter which pattern we add or do not add, we can always describe the data at hand. And if in the future we would see data drawn from the same distribution, we can always encode it even if the patterns have changed, right? Good. So these are the patterns. Then for each of those, we're going to have an associated code, which just like in earlier lectures, the more often we use this code, the more often we see ABC, the shorter this code is going to be, right? I'm going to use these colorful blocks just like this. But now, different than in the item set case, we will now allow for gaps within the occurrences of these patterns. So A, blah, 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 B, well, somehow we need to say that the blah, 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 we should not write the B yet. Whereas previously, if I gave you the code for AB, you could immediately fill out AB, right? So conceptually, we need some way to say like, not yet, not yet, not yet. There's many ways how you could do this. It's one of the differences between this ISM paper and the other 2 papers. And also, again, different in some of our more recent work. But here we use explicit code, like wait, wait, wait. Yes, you can write the next symbol. How does this work? Let's encode an event sequence just to give you a feel for how would we define the encoding, how many bits would this take. I have some data, and I brought a code table that consists of just the singletons. So the simplest base case. Then the encoding of this data effectively, well, for an A, we need to write down a code of A, for a B, and so on and so forth, right? I mean, this is trivial. So the pattern stream, as we call it, because these are pattern codes, is just verbatim, effectively the data. Now, what is the length of such a pattern code? Very simply, just like previously, I mean, these patterns will be independent, because if they are dependent, then they should have been combined, so they're independent. That means it's just a matter of counting and determining the frequency of these codes and using Shannon entropy to define what is the optimal prefix code length. So the negative logarithm of the probability of x. Note that here, so this x kind of could have a subscript, right? Because which distribution is it? Well, we somehow decided to use this explanation of this data using these. In this particular case, given that we don't have any patterns, there's no ambiguity. This is the only way to describe this data. But we will see in a slide or 2 that the moment we have a slightly less trivial code table, there is many different ways, right? So this probability is really according to the well, both the data and the way that we cover it. But we just have standard prefix code, no magic there. That means that the length of the code stream, so CP, is effectively, we just sum the code length of this one, this one, this one, and so on and so forth, or written like this, for every pattern in the code table, how often is it being used, times the length of the code for this. That's just a rewrite. Okay, let's move up, slightly more interesting. We have the same data, but I now have a code table where I also have a pattern ABC and a pattern of DA, right? Different encoding, different cover of this data, different explanation of this data, if you wish. Not necessarily the one and only, because there's going to be many different ones. Not necessarily, because I pulled this out of thin air, I mean, just for the didactic reasons, not necessarily the one that achieves the minimum number of bits, right? Just in case you wonder, but it doesn't really matter. What we have here is we have CP, so the cover, the codes for the patterns, and we see here a P, a D, an A, a Q, and so again corresponding to those. But we also have a gap stream, or gap and fill stream. And these are these exclamation marks and question marks that correspond to those codes. So how do we now decode this data back, right? Or vice versa, how did we actually encode it? Now, we start reading from the pattern stream and we read pattern P. We look at pattern P. Pattern P is ABC. Given that we just read this pattern, we can immediately write down the A. Because otherwise, why would we have read pattern P if we can't immediately act on it? That would be a bit weird. Okay, so we can write down the A, right? That comes directly from here. Can we now, for the next symbol, write down the next B? Well, we don't know yet. There might have been a gap. This is what we read then from the gap stream. It's an exclamation mark. Exclamation mark is a non-gap, or a fill as we call it, meaning, yes, we can write down B. Next, can we write down C? Okay, let's read again from here, right? We're still in the context of the blue pattern. We read a question mark, which is a gap pattern. Uh-oh, means we cannot write down the C yet. What should we fill out here? Well, that we just simply read again from the pattern stream. So this is now a D. We write down the D here, right? So this is why I overlap those. Next up, we have a fill symbol, so we write down the C, okay, and so on and so forth, right? I don't have to walk through all the rest. We are done now decoding pattern P, right? There was one gap in between. Now, what are going to be the code lengths of these gap and fill codes? Well, they can only occur within the context of a blue, respectively a red pattern, right? So we should not count them globally. So we can count them globally, but we should not divide their frequencies by the global number of fill respectively, but only the local ones, right? So how many blue fill codes, blue exclamation marks do we have divided by how many blue question mark plus, aka like this. So that again gives us a way to determine what is the total encoded length. We already know what it is for CP, and for CG, this is just analog, right? Note that the encoding scheme that we use here implicitly allows for interleaving and nested patterns. There's no reason why this recipe would not allow for, well, we have a, well, let's say in pattern P, there's a gap, and then we have another pattern P, and then, well, another, or a pattern C and a D and whatever, right? I mean, that is allowed. However, in this part of the presentation, we don't allow this. We don't allow nesting or interleaving of patterns. Mostly because determining the cover, so which code do we use where, becomes much more complicated. And well, this was a first paper of its kind, so we also have to be a bit kind to ourselves. Okay, but just mind you, the encoding allows it. Just like the crimp and slim encoding allows it. And also there, the cover function is what breaks it. And if only you would fix that, then, well, maybe we are in for better times, maybe not. Again, always, just as an example, right? We didn't write this explicitly in either papers, because why would we, right? The moment that you say to a reviewer, well, we could do lots of other things, then say, yeah, do it, right? And like the moment that you do it, then they're confused with the paper. So it's your job as the reader, as the critical reader, to figure out, hey, wait a second, what is now allowed here or not, right? I mean, is there more room for play? Okay. Total encoded size, length of the pattern stream plus the length of the gap stream. I'm going to skip the details for how to encode the code table itself. It follows pretty straightforwardly from what you already know from Crimp and Slim, and it's not so exciting. So if you now trust me that we also have an encoding for the code table, and well, we have now this one, we have an encoded length for the entire data and model, which means that we're done. We can now, if I give you a pattern set and well, the code streams, the cover of the data using, and I give you many, for each of those you can compute the code length, and you can determine this one is best, right? This is great, this is good. Okay, but suppose that I don't want to give both to you. I'm only willing to give you the set of patterns. But you have to figure out which pattern am I going to use where. Now, for example, here, with the code table on the right-hand side that we already know, we can still encode the data, just like the first trivial example, because we have those singletons. We can do this. We can also use one that we just saw, and then, well, two other examples. You would, and there's going to be exponentially or actually super exponentially many of these covers. So what can we do? And of course, we could do something greedy, right? We could just do something, but we're aiming for minimum description length. So I'm not sure. Did any of you do the assignment on Squeeze and Friends? No? Good, because then you are completely fresh in your thinking. What could we do? I give you a set of patterns and I give you the data. And your choice is your job is to come up with one of those and say, okay, well, this one is good, if not perfect. Good. Well, doing it optimally is out of the window. So there, I mean, I can go back to well, the item set case, right? Because there it corresponds to weighted set cover. Weighted set cover is NP hard, if not complete, meaning no luck, right? The best we can do there is a greedy algorithm, or the best, I mean, there we have a certain approximation guarantee. Otherwise, yeah. For sequences, this is not better. Let me just leave it at that. But still, we would like to be able to say, like, well, can we do something? Now, we had a thought, and well, in order to make this work, we had to split the problem into two parts, each of which are easier. This is a very general strategy that, well, I can recommend to, well, keep in your back pocket, right? And if the overall problem is too hard, break it into parts that are easier, and then we'll make sure glue these parts together or break it in a different way. So why is the problem so difficult overall? Well, the code lengths, or the code length of the entire encoding, depends on the code length of the patterns, and the code length of the patterns depends on the encoding. So we have a circular dependency, right? This is why you would really have to enumerate every possible super exponential. That's kind of shit. But if we now say, right, we, rather than solving the loop as a whole, we just start at one point in the loop and we fix the cover. Well, if we fix the cover, we have an initial cover that we can somehow deterministically just put down, and then we can count how often do we see every pattern being used. Then we can compute the code lengths. And then, as a next step, we can use those code lengths for those patterns to see, well, where should I use it such that I minimize the number of bits needed to explain this data using these patterns with these code lengths. Well, that in turn will give me a new cover for which, well, I again need to count how often have everything been used, i.e. I'm determining the new set of code lengths. And, well, rinse and repeat. And this converges relatively quickly. Is this perfect? Yine. So, no, actually, no, it's just no. What we can do, and what we show, is that if we fix the cover, we can find really the optimal code lengths. And if we fix the code lengths, we can obtain the optimal cover using dynamic programming. So in 2 steps, we are optimal. However, if we glue them together, well, we don't have optimality anymore. Because if I start with a really stupid initial cover, I can still have optimal code lengths. And for those optimal code lengths originating from the stupid cover, I can find the optimal new code. So if you start really badly, no way, right? However, with the ingredients that you're given, this is essentially the best that you can do. So you could call this a very smart, greedy algorithm, given that it doesn't just blot things wherever, but there are some guarantees there. Good. So this is how we go about this. And as the initial code lengths, we explored a number of different strategies. One that works remarkably well is to have the initial cover, basically a pseudo cover, in the sense that we simply count for every pattern, how often is it being used? Or is it seen in the data? For every pattern in the code table. How often is it seen in the data? And then we just play pretend those are the code lengths. That is not a valid cover, but it is something we can deterministically determine, and it also gives shorter code lengths to shorter patterns, or to more frequent patterns, typically also the shorter ones. But that is fine, that is shorter. Because during the cover, I mean, if we have AB is very short and then C is a bit longer, yeah, AB, the code for AB plus C is likely still going to be much longer than using directly the code for ABC. Also, the chances of getting on the local level shorter code lengths than using the pure occurrence numbers in the data, well, that doesn't exist. It will converge to that. So that is the starting point that we use in one of the variants of the algorithm. Good. It means that we only have one final problem to left solve. How do we find a good pattern set? Well, the basic idea, actually right now, back then when I was presenting this in Beijing, I could not say so because people did not know what SLIM was, and I'm not sure even, I don't think SLIM was published yet even. But now I can say, let's take the idea of SLIM. We're going to exploit meta patterns, patterns in the usage of patterns. So, because if there is any patterns left in the way that we use patterns, this is unmodeled structure. For example, here, if we start with the encoding of the data just using the singletons, then if we now find the most, let's say that pattern of either length, let's actually just length 2. We only want patterns of length 2 between codes. That is most frequent, counting minimal windows. Well, AB happens a lot. Let's add it to the code table. Okay, we have a new code stream, right? Because you know how to optimize this and so on and so forth. This one wins, right? So we're happy, it stays. Well, next up, what do we see? Well, here we see CD happens a lot, right? I mean, twice in this excerpt. Okay, so we add the next pattern, and so on and so forth. It could be that we say, hey, well, PQ happens a lot. Let's add a pattern R that basically integrates them, and so on and so forth. Very simple. But the idea being to iteratively look for redundancy. Effectively, generate all pairs of codes for a given code stream, estimate how well would they, in the best possible universe, the best possible turn of events, help to encode the data. If that estimation is already bad, well, we kick it out. We already truncate the computation if we see, okay, this is not going anywhere, right? You could even be more aggressive and start to compute or try to figure out which pattern is going to be best, in the sense that we expect it to give the best gain in compression. And for any other candidate that estimate is worse than the current best one, we already stop, right? We can be very aggressive there, because otherwise, well, there is going to be very many possible patterns or candidates. Yeah, okay, sure. The first strategy, what we could do is that we generate all these, blah, blah, we order them in estimated gain, and then, well, test this batch. And the other is that, well, when the batch is empty, regenerate and re-rank. So we can either do it like all the time, right? So we generate the best candidate, see if it works, and then start immediately again, or we generate a batch, and then, well, we filter to this batch, which is computationally much faster to generate these candidates, because in order to find the best single one, we probably need to regenerate an entire batch. Why would we throw this out, right? So, this gives us then squeeze search, which is I just took the graphic from SLIM and I changed some names, but otherwise there's nothing different here. And we can also do the crimp variant, where I first mine candidates, I order them very similarly, and then we just give them one by one. That gives us these two algorithms that perform like this. We have squeeze search, the one that you just saw, right? Slim squeeze, so to speak. And we have squeeze candidates, squeeze crimp, if you wish. Higher is better. That's the number of bits gain, the delta. And this is the iteration in the search. So, as you can see, squeeze candidates, well, does quite well. Squeeze search has this bump behavior because it generates these batches, right? So here at the end of the batch, yeah, it's basically not getting good candidates, but then it gets good candidates, right? So, and as you can see, in the end, it's a bit higher than squeeze candidates because, well, squeeze candidates might have kicked out candidates at one moment because right now I don't like it, but then later it might have needed it. Plus, squeeze search might have picked up some things that are quite rare and did not even appear in the candidates list without making the candidate list really explode beyond belief. Okay. Both work essentially equally well at this level because recall, compression is not really our goal, right? I mean, it's a means to an end. Okay. We have some experiments, of course. Let's start with some sanity check on random data. We don't find any patterns. That is good. I keep repeating this because you don't want to know how many papers out there don't check this. And if you then do it, then all of a sudden you find all sorts of results. And yeah, you don't want to have false positives. We can generate data using a hidden Markov model, right, where we really know the structure. Hidden Markov model is, of course, not really the type of structure that we're trying to find, right? I mean, if you have data generated by an HMM, you should fit in HMM. But the paths in the HMM can correspond to patterns or do correspond to patterns, so we can cover this data. But we will cover exactly the structure. Then we also looked at some real data, all sorts of different things. I could show you the alarms data, but you don't know what these alarms mean, and I'm not allowed to tell you too much except for the general onset of it. So we will look at text data. Is text data the best type of data for evaluating these types of measures? Not really, not really. Text is very ambiguous, right? Words have many different meanings depending on context. It's very diverse. You can use very many different words to express the same thing, like mum, mama, mummy, mum, and so on and so forth, right? I mean, well, these are now 4 different tokens, right? So yeah, how do you even pick this up? Good. Just for 3 examples, database of residential addresses. Perhaps you remember from the crimp lecture that I also showed some meta patterns there. JMLR, Journal of Machine Learning Research, abstracts, and the novel Moby Dick. These are the alphabet sizes, so number of unique tokens, so quite reasonable. Number of tokens in the data, also quite reasonable, at least much more than you would like to look at by hand, right? And mind you, this is in the 2012, I think, so we're not really in the scaling up LLM style. But even then, right, if you would like to do this right now, good luck. How many frequent episodes? I think the minimal frequency here was 10. I'm not 100% certain, but tens of thousands easily. More than you can shake a stick at, you don't want that. Squeeze search finds a few hundred. Still a bit too many if you ask me, but yeah. If we are fair, the pattern language here is very restrictive, right? It really is like A and B. And if we have this, well, mum said, mama said, and so on, well, we're going to have 4 patterns. So it explodes, right? And she can say stuff, she can shout stuff, and whatever, right? Whatever mums do. I mean, that's lovingly say, I mean, of course, it's mum. Good. What are the results? Just some, well, these are the top 5s. For JMLR, well, support vector machine, machine learning, state-of-the-art, yeah, all makes sense. Presidential addresses, United States, take an honest, solemn, whatever oath, right? Always some adjective. We speak about the Army and the Navy because, well, we're in the US and, well, here's your freedom, and so on and so forth. Okay, that was 2012, right? Let's move a little bit forward into time. So, 4 years. I was working with Apertim. Apertim was a student in grad school. And he wanted to do a research immersion lab. He liked algorithms, he liked sequences. Okay, let's go, let's roll. And we looked at Squeeze and we liked it, but it's also like, it's so limiting, right? I mean, exactly this A, B, C. So let's try to get this pattern language a bit richer. we put on our thinking cap, and we thought, okay, well, this case, so this is, let's say, well, okay, I don't have an immediate example like with mum or whatnot. I mean, that's, let this be mum and this is mama or whatever, right? I mean, something like this. But, rather than having two patterns, this would be nicer. A, B, or D, C. This is something for which no name existed. So there's serial episodes. There's also parallel episodes where so in a parallel episode, both B and D are happening, but the order between them is undefined. So that's not really what we have here, right? It's really the one or the other. So we call this a choice episode or a choice-isode, which is perhaps the most horrible word I came up with. And for those who had to do this assignment, had to write choice-isode or had to speak about choice-isodes, I do not regret. We also thought that this could happen. ABC, ABCD, where ABC is a prefix of ABCD, obviously. Now, it could well be that you start, I don't know, watching on Netflix, right? Let's say just one series, right? I mean that's and you watched episode ABC, right? 1, 2, 3, and afterwards, like, okay, well, either you got distracted or perhaps it was not your thing, and if it's totally your series. So you also watch D, right? I mean that. How many patterns do we need to express people watching a substantial amount of episodes from series X? But of course, also more interesting is that, well, let's say this could be seasons, right? This could be, or seasons of different series and whatnot. So people can have different journeys over these things. But how many of these sub patterns do we now need, right? Do we also need, well, BC? Do we need AB? Do we just need A? Perhaps if there really is one episode or one season after which people say, like, yeah, no, this is not my thing anymore. We need not a choice episode, we need a stop-isode. So we have choice-isodes and stop-isodes. Well, this is where the things that Apartim and me started to look into. Can we find these three types of patterns? Second, we didn't like that squeeze does not allow interleaving and it does not allow nesting. Well, we already discussed that in theory, the score can do it. For this, I can also give a small anecdote. When I presented Squeeze at an information theory conference back in 2012, I suppose, I explained what we were doing, that was this code, and then I said, well, during the cover, we do not allow, explicitly do not allow a pattern AB inside another pattern of AB. So effectively, we are, well, not calculating the optimal code lengths. Because if within AB I do not allow AB, but I still use, let's say, well, the code length for a C and a D, right? I mean, that which code lengths do I use? I mean, I just use the global count of C and D, but that is not entirely fair. Because if AB or any other pattern is not allowed to happen inside AB, I should not use the overall counts for C and D. I should use only the counts, the possible usages of those patterns I could possibly use. Otherwise, I'm wasting bits. I'm wasting probability space, I'm wasting code space, right? So I explained this, and I had a room full of like 50, 60 people, and explained, okay, that it was really 50 people, right? Really high, big names in the information, all saying at once, ooh. That was the strangest experience that I had, except for one. But a room full of people that I deeply respected, ooh. Because, well, it's minimum description length. It's not, well, approximately minimal, just when, in the end, I mean, I managed to convince them that by going fully minimal, we're actually not going to find the results we want. Because what we saw that happened during the search, because there's a very weird interplay, that suppose that we don't have some stretch of data, right? There is some really just noise, right? This is just noise. And then there's the one symbol right before the noise and the one symbol right after the noise. And by just calling this now a pattern, let's call it AB, just for the sake of the argument, right? AB happens once, and maybe it also happens a few more times, right? I can always break the argument a little. I'm using AB just to indicate here is noise, which is not the semantic meaning that we want from a pattern. It's also why I said, well, I can break it a bit further because, well, you could say, okay, well, we need it to happen more often than just once. Okay, now we have a number of stretches with noise. 3, 4, 5, whatever, right? I mean, is AB then, if it's truly now begins noise, now ends noise, that's a different story. But so effectively, what we found for certain data sets, it found the first symbol, the last symbol, and it was done. Because the search doesn't allow nesting, so you found stupid models, so we didn't want that. Good. Yeah, let's continue. We want better covers. So squeeze, non-overlapping, non-nested, non-interleaving. And what we want nesting, because why not? Well, the reason why not is that in the dynamic programming optimal cover, that it breaks it completely, nesting. There you really need to have basic, then your table explodes in so many ways. We couldn't make that work. So that's the reason why it didn't happen. So, okay, we wanted nesting and we also want interleaving. So this pattern goes span, so where AB or DC, depending how you look at it, goes over the interleave. And then we went from squeeze to squish. Squish is yet again just a name, right? Doesn't stand for anything. I mean, we can always backronym it, but I'm not in that business. So squish is to find, well, using a richer pattern language, better covers. And well, we came also up with some ideas to speed things up quite dramatically. So the time that squeeze needs for these data is 5 minutes, 8 minutes, 46 minutes. The same compression, right? And then we hold it for squish, 3.9 seconds. So this is really orders of magnitude faster. This is good. If we just let it run until it converges, then it takes a bit longer. Meanwhile, we have fixed this because, well, basically it gets stuck in testing many candidates for which we already estimated it will give, let's say, 0.001 bit gain, and then it doesn't, or maybe it does, but we don't want these candidates. So using a smart information theoretic significance test, we can weed out this, and then, well, runtimes are essentially just fractionally longer than this. What is also nice to see is that the compressed sizes, so the gain in bits for squeeze, 5.4, 29, 9.6, squish beats it all the time. This is with interleaving. With choices odes, we beat it even more. So, which is good because, well, this is why we don't want these things just to be like synthetic sugar, right? But we can express more things. Okay. So with richer patterns, so these are the serial patterns that serial episodes we saw. Choices odes, some examples for JMLR. So empirical versus structural risk minimization, independent or principal component analysis, and so on and so forth. This is just by throwing squish with the choices at this data, as the JMLR data, and it picks up these things. I was very happy with this. Because squish, of course, doesn't know anything about semantics, right? It doesn't know anything about concepts. So it has to come from the data, right? But having this grouped so neatly, even if you don't know what Mahalanobis distance is, but well, you do know what edit distance is, if these are really used in similar ways, in similar contexts, there you are, right? I mean, so this was really, really nice. What we also looked into, the stop episodes, we didn't find so many. We found some, but they were not really exciting or so. I mean, there we, at one moment, I'm not sure if I mentioned this at another slide, Margarita Salieva did a master's thesis with us a few years ago. And there we looked into skip episodes. Well, now you know immediately what this does, right? I mean, that's so is this a good name or is this a good name? It's perhaps not so serious, but hey, you can skip certain things. Maybe you're not buying Harry Potter, let's say the 4th novel in the series, because, well, your aunt gave it to you, right? Well, that doesn't make you, like, all of a sudden not support the Harry Potter series, pattern, right? But we should be able to skip certain things. The moment that, well, things are skipped too often, then, of course, it's a different story. What we also looked into, this was with Katrin. Katrin afterwards did her PhD at CISPA, is now with IBM in Zurich. She so she is a computational linguist originally by training, and she was interested in, well, ontologies and the semantics, right? And so this is before we wrote the Squish paper. But there we're looking at patterns of, well, this shape, where you see that this is a big A, this is a small b, and this is, well, a curly C, or an even bigger C if you wish. Effectively, what we now did, we had the data, text data, and we used a, what is it? A POS, part of speech tagger, right? So basically for every word, what is it, right? I mean, is it a verb? Is it an adjective, and so on and so forth, right? I mean that. And now we had different layers of this, different levels, and now we allowed the pattern miner to basically build patterns over each of these levels of the hierarchy in order it should still reconstruct the data as we saw it, the original tokens, but it can use higher level patterns if you wish. And then we found stuff in like Lord of the Rings, like, well, he, verb, conjunctive, he said that he. So we find really structures of speech that are quite common, right? I mean, so he said that he, or he did that, I don't know, I mean, that's, but anyway, so there's multiple instances, otherwise it would not have used a verb here, then it would have just gone for said, right? So there is really different levels of abstraction there. Perhaps not like the most shiny examples, but that is fine for now. So that was in 2016, right? So, okay, yeah, that was it, right? I mean, let's go to 2020, because we've been dwelling in the faraway past for too long. I was talking to a professor here on campus, and they were looking into earthquake data. So there was some project, and effectively they wanted to predict earthquakes. And I told them, good luck. Because from all I know from other people who've been looking into this seismic data, it's horrible. It's horrible. The measurements are horrible, and then, well, you have a truck driving by, and that's whatever, right? I mean, so no. However, it did set me thinking, because if we abstract away, and abstraction is the business that we're in, an earthquake is an interesting event, right? I mean, it can be quite destructive, right? But it's definitely an event of interest. Let's call it that, right? Now, we could try to find event sequences that predict that an interesting event is coming, right? What we effectively could do, if you just envision it, we have a regular event sequence, and we just insert all the interesting events, right? So we have a symbol earthquake, right, somewhere, right? And then we have ABC earthquake, and we can try to find patterns. And then we can interpret ABC, and then, well, if earthquake is the final symbol, okay, that is then going to be the pattern, right? Okay, we could do that. What could possibly go wrong if we would do something that naive? Well, many things. First of all, by just restricting the patterns we are interested in finding to include an earthquake in this case, we steer the search process very much like, okay, look for this rather than describing the data as a whole. If we do allow it to find any pattern and just look into those that include earthquake, well, it's very unlikely it will find something with earthquake as the tail, right? Because, well, after earthquake, lots of things happen and will be included. So, we should also think a little bit, what does a pattern express? Just that a certain sets of events happen in a particular order. It does not mean really truly what we're after, namely that if we see ABC, there is an increased probability of getting an earthquake, because there will also probably be plenty of ABCs where earthquake doesn't happen, right? So we are not really interested in an event sequence pattern, but more of a rule type of thing, right? ABC, then something is going to happen. Okay, that's the first thing. Another thing is that, well, suppose that we would use the traditional stuff where we have strict subsequences. Maybe we can find that ABC increases the chance for an earthquake. But it's kind of shit. Like, okay, there's an earthquake going to happen in 5 seconds. I mean, no, right? I mean, well, it would be great if we can predict it, but it's kind of useless. It's not actionable, right? We would like to have. Now, we, of course, have the advantage that we do allow for gaps. But we also like our minimal windows, our patterns to be relatively compact, which sort of breaks this entire thing, right? I mean, that's we would like to have the pattern part to be reasonably compact, but that the interesting event, in a way, well, how far away in the future, we don't really care, except that we do. There's yet another twist to it. Because if I say, if ABC happens, there's going to be an earthquake in the future. With 99 or 100% probability or whatnot, right? I mean, then what? Your question is going to be, when? When, right? Like, well, in the future. Don't you have a bit of excitement? No. You would like to know, is this going to happen in a week, in a year, in a day? I mean, right now, right? I mean, So you would like to have a predictable delay between the, let's call it the head or the antecedent of the rule, and the thing happening. So we are in a way close with what we've seen, right? But we can't use it directly for finding patterns that really lead up to interesting events. We need something different. So then, this was in 2019, 2020. I think Joscha started late 2019 with this. Joscha Kuppers, I mean, he just handed in his dissertation, so let's say the story was a success, you could say. But back then he was doing his master thesis. And these are actually, I'm using verbatim the slides that came out of this project when we published it. So he's very good with making pretty slides. So we have an event sequence, X, just like we had before, right? This is where we want to find the ABCs. And we also have now conceptually a different time series or event sequence, Y, where 0 means boring, 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 and 1 means, interesting, right? That could be a specific event that we're interested in, right? I mean, that is also in X, right? I mean, then we could take it out there. Or it is really like, okay, earthquake or something external. So the task is really, can we explain the occurrences of the interesting events using X? In a way, what we're doing, another analogy that you now can see, we're doing in a way some form of perhaps subgroup discovery. It's not exactly subgroup discovery, but it kind of is, right? It's a set of conditions on X, on the regular observed data, that gives a different distribution in the target. But it's not subgroup discovery as you know it. Okay, for example, here we have then, well, I'm compacting things, pattern CE. And CE, as you can see, predicts interesting events quite well, right? I mean, that's so after every occurrence of CE, there is an interesting event happening. Well, this one is unexplained, but fine. We can look at what we call the delay distribution, right? For this pattern, CE, and this mapping, right? And yes, we will need to find these mappings ourselves. This is where things get hairy quite quickly. We can simply count how often is there a delay of 1. So it's once, twice. So here, how often is there a delay of 5 and one delay of 8. So this is the histogram, right? Okay, we will need this because we also have other patterns, for example, AB. AB predicts exactly the same set of interesting events. However, AB does this in this particular mapping, right, for every occurrence of AB with just a delay of 3. Well, that is much more predictable. So the notion that we're using to determine this predictability is looking at the entropy of the histogram of the delay distribution, right? And there we see that AB wins over CE. So that one is better in this particular case. So if we have two competing patterns that explain the same set of interesting events, then we definitely go for the one with the lower entropy. If they don't exactly explain the same set of interesting events, well, then we have a bit more of MDL magic, right? But in this particular case, you would really like to have a predictable delay. There are these other two interesting events that AB does not explain. What do we do with this, right? I mean, well, like I said, a bit of excitement in your life, right? I mean, is there an earthquake going to happen? Can we also explain those? Well, hopefully we can. So actually, there exists also another pattern with a predictable delay. I mean, delay of 1 in this particular case, so it's not super useful, but okay, it is something, right? I mean, that is then EF. Together, EF and AB explain the interesting events here, well, perfectly well. It's of course the ideal outcome. Might be that some ABs, there is no interesting event following, right? Or we didn't record it. Could also be the other way around. There are some interesting events that don't have a pattern-based explanation that we can pick up, right? It's also possible. So what we're interested in is to find a set of patterns with a delay distribution, each with its own delay distribution that allows for reliable and actionable predictions. So this is what we started with Josha's thesis project, his master thesis. And note this is, well, we took the earthquake thing as an example, and good luck doing this with earthquake data. We didn't even attempt, right? But we sort of put it around and like, what are now the tricky things and what is now the true problem here that you would like to? And this predictable delay, maybe depending if you hold them upside down or something, you will find some papers that do something in that line, but most do not. Most just focus on, can I predict something at all? This brings me to my second most favorite question. I mean, the so what, or what is it useful for, right? What is the true question? And if you have a hammer, everything looks like a nail, so we're going to do prediction, but do you just want to predict or do you want to do something else, right? Question, always question. Okay, so what is the length of a model? I already gave that away. I mean, actually, well, no, that part I didn't give away. So we need to describe the symbols, EF, AB, for each of the patterns in there. Okay, fine. Then what is the length of a pattern? Okay, fine. These are these delay distributions. We want to have the intuition that CE is worse than AB. That's why we look at these entropies. But we don't use entropy just plainly. What we actually will need to do, we need to transmit, right? If I want to use the model where if AB respectively CE, you need to know these delay distributions. Otherwise, you don't know what the options are for these delays, and then you don't know what codes to read. So I need to transmit to you the data underlying these histograms. Meaning, I need to tell you how many bars are there? 3. What are the delays corresponding to these bars? 1, 5, and 8. Monotonically increasing, right? I'm going to do this in the right order. And I need to tell you, well, how high are these bars? So this you can see as a combinatorial problem, where it's just, okay, we have 4 beads, and well, 2 beads go into this bin, 1 here and 1 there, right? And here, all 4 go into that bin. That is the intuition of the encoding that we use. We just translate that directly into bits. Intuition of an encoding is always, what is the information that you need? Transmit it as compact as you can, and you're done. Right? That is your prior. It's very important to realize this is a prior. Right? I mean, all what we're doing is just it's essentially Bayesian learning, except that we don't take the prior out of the big book of priors and then hope for the best. No, we think about, well, what type of biases would we like our prior to have, right? And then build it in, rather than we take something and then, well, what biases do you have? Do I like that or not, right? So it's a bit more focused on what we want. Good. In essence, what it comes down to, the fewer peaks we have, the better, right? Or the fewer bins we have. Okay, so how do we now determine how we encode the data? Let's start with the pattern AB. For the sake of the argument, right now, and also in the very first edition of the paper, we did not allow gaps within these, well, the pattern parts, within the ABs. Trivially implementation-wise not, but trivially extendable at the conceptual level here. Doesn't really matter. What we do, we look in X and we mark every minimal window where we see AB. And if we don't allow gaps in the minimal windows, it just becomes subsequence matching, so you're done. And we generate this sequence, this Z, for a particular pattern S, sequence S. And this one is always 0, except for when a pattern has been seen, then it's 1. Right? So we get ones that, effectively you could say this is the hook, this is the call or whatnot, right? Yes, I've seen AB, right? And that we can use to start saying like, oh, well, how long till the next earthquake or the next GLS truck coming by? So we want to map ZS to Y. So this one, right? I mean, how can we map this sequence to that sequence? Well, first of all, there's 4 ones here and there's 6 or more there, so we can't do all. So we need an alignment, as we call it. So we need to determine which of the ones in Y do we now explain. For that, we have an algorithm that maps it essentially to the closest one, right? That's the first step. And then, well, there's some algorithmic magic to update things. But by just mapping into the first interesting event, we already get here. This is a delay of 1, this is a delay of 2. This one, it could map to here, but this one already maps to here shortly. So we call this a skip. Skips are effectively an infinite delay. This is how you can intuitively see it, right? So it's yet another column in the histogram, right? The skip column or the infinite column, fine. It's kind of like noise. If too many occurrences of AB do not predict anything, we have many skips, well, that makes AB a pretty bad predictive pattern, right? Good. Okay, so this is then the alignment, and this maps to these three. Also means that we still have three others that are not mapped. Right? So you could see that the alignment is sort of like a pseudo Y, right? But this one has a 0, and it should be a 1. So in MDL, we want to reconstruct the data as is. We don't want to make things up, right? So how do we now get to the actual data? Well, we have a residual stream. What is the residual data? This is basically just y hat x or y, then we arrive at r, or y hat with r, then we arrive at y, same thing. Effectively, these are just the remainders, right? So the ones. That one, so what we do is that if I give you the set of patterns, let's say AB, and I give you the data, because the data you get for free in this particular example, you can find where do the ABs happen, you can determine where the Zs. We will have to then do the alignment algorithm define y hat, and y hat together with y gives you r, right? So the only thing I need to tell you is AB, and I need to tell you the residual. Otherwise, you don't know which ones to map to. The residual, what we're going to do is we're going to use a very simple frequency-based encoding, prefix codes. So the more frequent a symbol is, the shorter the code. Well, interesting events are by definition rare. Rare means long codes. It means that there's a lot of, let's say, evolutionary pressure, if you wish, to get rid of ones in R. But in order to get rid of an one in R, you need to have a pattern that, well, maps to the right ones. And so this is basically the dance that we're doing. Okay. How do we find a good alignment? I already gave away much of the magic. The first step is that for every one in Z, we map it to the closest interesting event in Y. Well, we have some clashes like here. So the clashes we remove, and which one do we remove? Well, we look at the histogram that we have, and we remove that edge, the clashing edge, with the lowest probability. That's this one, the 1 delay, right? So we get rid of this one. Why do we do that? Because we want as single peaked distribution as possible. So we want to get rid of the lower peaks, right? So now we made it a bit better. So this becomes a skip. Apparently some font issue. But now we need to think, can we maybe reassign things such that everything becomes even better? Well, yes, we can now reassign this one by looking at what are the biggest peaks and which are the options. If I now reassign this one to that one, that's better, right? Okay, now we have next iteration, same thing. This one, so this one has now 2 incoming edges, but if I get rid of this edge and I move it to there, and there we are. Now we have a single peak, best possible setup, right? I mean, even though we started with a more complicated distribution. Isn't that great? So this is how we find alignments. How do we find pattern sets? This is where one of those, despite having now, when did I start my PhD? 2000, almost 20 years of experience, I mean, almost, where this is going to be simple. It's not always true. So originally we thought, okay, we're going to use SLIM. We just start with the singletons, and there we go, right? We just combine them as that has worked here, fine, right? I mean, it was not fine. Because the problem was that all non-compressing patterns will have the same MDL length. And we essentially don't get any signal, like something is good, unless we're already very close to the true pattern. Then we can optimize it a little bit. But we need to have a sizable chunk already. Now, the singletons are typically not enough for that. So we were kind of stuck. However, when you have a combinatorial problem And well, a simple heuristic doesn't work. You say, okay, well, screw it. We're going to go for something with guarantees, then branch and bound, right? Subgroup discovery. We've seen this, right? And that's so sort of like the magic wipe for combinatorial problems. Well, rather than doing pure branch and bound, like really with the guarantees and admissible tight optimistic estimators and blah, blah, well, we can take the idea of optimistic estimation. So if I now look at the occurrences of A, right? Suppose that there's a true pattern ABC. Now, A happens much more often than ABC. Let's do that, right? And same thing for B, same thing for C. This is why we really need to combine all three. However, I can look at, okay, what it would be the optimal assignment of A's to interesting events, where I'm allowed to completely ignore any A that I don't like. Effectively, I'm thinking about, well, there's going to be some other event, B and C, right? That if I combine, then I would just have exactly this. I can reason about what would be the score for that best possible pattern. I don't know yet, right? But I can, of course, if A happens, let's say 100 times, and like super far away from interesting events and whatnot, then yeah, it's going to be a shitty pattern no matter what. But if there's, let's say, 10 interesting events, 100 A's, and there are 10 A's that map beautifully to these 10 interesting events, well, it's just a matter of getting rid of the stupid A's. And we don't know yet if we can, but that's the whole magic of branch and bound, right? We're optimistic. Let's just live in the world where we can. So that's the idea that we implemented. We have sort of a look ahead type of score, right? That tries to look optimistically. And then, well, we see if by combining, adding a B, adding a C, and aha, okay, well, maybe we now have 11 occurrences of ABC, but they explain 10 of the interesting events, everybody's happy, right? It's not as good as we would have hoped, but hey, come on. So, yeah, we start with an empty code table, so to speak. We search for patterns using this optimistic estimator. This is the estimator. We generate these candidates. We select one. We add it to the model. We, well, determine, right, like MDL determines, do we keep it yes or no? We generate more candidates, and so on and so forth, right? So basically, it's again a slim variant, but now with a smarter look ahead that we never needed in the simpler versions. But it's still interesting to see, well, what could we do if we were to include it? Because slim does get stuck in, well, smaller patterns. If it could in one go find the bigger ones, that would be amazing. Same thing for grab, same thing for, well, squeeze, and so on and so forth. Okay. Does it work? We needed to evaluate a number of things. Because first of all, we have a score, a new score. Like, can we explain interesting events well or not? But, so for that, so we also did this on completely random data, but it's not so interesting right now. We compare to two methods. So there's CUTE, that's a causal inference-based method that Kailash and I developed a number of years before, and TENT, this is transfer entropy. So good names, I would say. In the data, there's 50 truly predictive patterns and 25 patterns that are frequent, but not predictive of the interesting events. This is how we generated the data, right? And we give them one pattern at a time or a set of patterns, whichever they want, and basically have to say, okay, well, now map things, right? I mean, how well can we predict the interesting events based on? These are where these red and blue lines are, an accuracy of 50%. Well, not great, you could say. Why is this? Well, partially because there's destructive noise, because otherwise life is a bit too simple. So the true ones, this is again a bit of a mismatch. Well, why did this happen? So this arrow should be here. So basically we kill a number of the ones, right? We destruct them. We also have additive noise, where again, alignment error. There we add a one here, and add a one there. We just flip some values, right? So that is what destructive noise and additive noise does. So we go from 0 up to more. But well, yeah, if it's already at 50% with no noise, then well, what can we do? We can also equip these scores with our method, which, well, you see that basically it doesn't do much. And we can also look at our method as a whole. equipping the other scores with our method is basically determining which events do you want to predict or not, right? So it should, okay. You can see that at the tail end of high destructive noise, high additive noise, when things start to break down, you might worry about that. We'll see that in a second. Okay, now, if we actually also include the search, not just the score, right? Because we could now pick up which patterns were predicted versus weren't. That was the task in the previous slide. Can we find such patterns? Now, what we have, Omen, this is our method, squeeze for finding patterns, then using Omen to pick up which ones are now predictive, because we now saw that Omen is pretty good at that. And we have for SCIS, that's a competing method that is supposed to solve this problem by itself. That's these blue dots over here. So let's not pay too much attention to that. If you look at this plot, what you see, besides that, of course, we win, whoo, yay. You also see at least two interesting things. You see that, well, we're better at destructive noise than additive noise. Additive noise means screws us over much more badly. But you also see a very steep drop-off at a certain percentage of noise, right? It's really like, yay, everything is awesome shit, right? And well, okay, here everything is awesome and then shit. Where does this come from? So if we combine things, it looks like this. So this is both additive and destructive. So well, basically as bad as the additive noise. I mean, nothing too much. What we looked at to investigate what is this weird drop-off, right? Is this now good? Is this bad? Because it doesn't look good, right? I mean, now we know, of course, what the true model is that we generated the data with, right? So we can, for a given data set, we can just, well, give the real patterns to the method. We even know what the correct alignment is. So we give it as well. And then we can compute how many bits does this cost. This is the green line. Well, there's also a null model. Null model is there's no pattern. All interesting events are completely independently generated, right? We can also compute that, the black line. And then you see that something interesting happens because there's a crossover between the black and the green line. So there's a point where the true model actually performs worse than just saying, okay, there is nothing to see here. So the true model is not identifiable here. It is actually really literally a worse choice than saying there's nothing here at these levels of noise. And now it's interesting to look at the orange line. The orange line is the line of the model that we discover. And as you can see, okay, sure, I mean, we have a slightly higher encoded cost, right? So we don't find the perfect model. There is some gap, right? So there's still some room of improvement. But yeah, the moment that we hit the black line, our method is sane enough to say, okay, well, there's nothing to see here. So that is exactly this point around, is it 40, where things really sort of, there's just nothing here anymore. So yeah, this doesn't look great, but actually this is just theoretically the best possible you can do. There's nothing to be discovered anymore. The moment that we would have, well, higher than 0, hello blue line, higher than 0 F1, this means that, well, we're only just spitting out noise for which it's really literally impossible to say if it's true structure or not. And that's exactly what SCIS does. I mean, it basically returns all the patterns, almost all, and yeah. So this is an example, this is why I included it in these slides, where sometimes something that doesn't look so great actually has a perfectly fine explanation by which you just see, okay, well, these are just the limitations. And of course, you can always be unlucky and get a review like, oh, but I want you to do better. Like, no, you can't, right? We could have chosen, and many people do, to just show the results up to, let's say, well, 30% noise, something like this, up to here. Because 50% noise is not realistic anyway, right? We literally chose not to because, well, even though 100% noise, yeah, there's nothing to be found. But what are the limitations of your method? When does it start to scream in agony, right? And this is important to know because the moment we do run your method on some real world data, we kind of want to know what is the behavior. Now we know. Can we find long range dependencies? Because this is what I started, right? We want to predict not that A, B, C, and then now, right? But also, so for this data, we generated the delay using a distribution with a mean of 50 and a standard deviation of 24. So basically what you're looking at here. The ground truth delays are the black ones, and what we now found are the red ones. So it's not perfect, has a very slight bias to the left. You can see that here it's a bit higher than black, and here it misses out a few. But I would say this is a pretty good reconstruction, right? That's so good. Delay distributions. On real-world data, let's actually quickly go through that. We looked at a number of different things where, well, also delays need to make sense. So we looked into river data, river flow data. So if there's, let's say you have multiple stations across Germany, if there's a big flow coming in from, let's say, from Switzerland, then it will go downstream, and at one moment it will leave Germany again. Can we detect this? Or in this case, we look specifically at the Saar, but I mean, same story. Live loggers data. I mean, these very special kind of people that literally write at every time of the day, what are they doing? I entered the classroom, I exited the classroom, I went to the toilet or not, whatever you did, and so on and so forth, right? I mean, then you have event sequence data, and then, well, you can mine patterns on that, or I don't know. It's special kind of people. We find patterns that with certain delays, that cooking can take lots of different steps. This is really like cutting the onion to going to buy an onion because I forgot the onion, leads to dinner, and dinner then leads to cleaning the kitchen. But sometimes there's plenty of delays in between and whatnot. We can also look at ECG data, where, well, sort of like we had, I forgot now the words. What is it again? Basically, there's this contraction of the heart chamber right before it has the actual. Well, this is what we can predict in that. Plus, and this is interesting. I mean, so what you can see is that here, so the typical delay is 10, 8 and 9, okay, this is during sports. And there were a number of anomalies. 43 is not good. But this is exactly that, well, why this patient was being ECG'd. So there was a particular arrhythmia. I mean, that's, well, picked it up. So it's good. That's good. Okay. That was it for today, more or less. Because what we've seen is that by breaking IIDness this time, by having time, we can start to reason about patterns over time, dependencies over time. We saw a number of different ones. We saw the notion of a pattern really like A happens then B then C, right? With or without gaps. We've seen that it's much more difficult to even count how often does something happen, right? Not sure if you expected this, that it becomes more difficult, but it does. We've seen how we can find models, these compressing-based models, right, to find what are now the key patterns. We've seen how we can extend these pattern languages, because just these simple conjunctions. I have a bit more to say on that in a second. Then, in the second half, with Omen, we saw effectively how can we start to put this to use. I say start because we can't really predict earthquakes with this, right? But we are really taking a step from what is just a pattern to really what is an interpretable model that has use, right? What is, and this is what I'm particularly proud of there because of this delay distribution, it is somewhat reliable, it is actionable. It's not just something is going to happen in the future, right? I mean, that's everybody's going to die. Yay, yeah, okay, we knew that, right? But I mean, how long, right? That's kind of important information if you make predictions like that. So we saw squeeze and squish for summarizing sequential data, complex problem, fast heuristics, and we saw how to extract good models directly from data. And for Omen, these reliable temporal prediction patterns, complex problem, fast heuristics, etc. We have done a lot more in this domain, a lot more than I can possibly have squished into this lecture. I mean, I was tempted to really flashcard many things, but I decided against it. So I'm going to abuse this slide. I could have discussed Cascade with you. Cascade we presented last December at NeurIPS, and Cascade effectively takes Omen, the idea of Omen, of these reliable, actionable prediction delays. But rather than thinking really in patterns, it's ABC cause an interesting event. What if we now consider every event, A, B, C, as a different variate of interesting events, right? So we have a variate X, A, X, B. This is how you can think of it, right? Which is 0 if A doesn't happen and B if, or in 1 if it does happen. And now we can start to think, okay, can we now determine causal dependencies between them? Does an A cause a B? Or a B together with an A cause a C? That's the next level question we didn't even answer. The idea there was in networks, you have networked devices. And well, if let's say some switch or some router starts to go haywire, that typically causes an error in other devices as well. Can we, well, lay out from such network data, which is event sequence data, just that, can we lay out the causal network and therewith do root cause analysis. That's what Cascade does. Effectively, it takes Omen, well, removes some parts and builds on top of it. So complex problem, fast method, and it has guarantees. So for that one, that's the exception here. We can also include Flock. What does Flock do? Flock is, in a way, Squish on steroids. And Squish on steroids in the way that in Squish we had these choice zones, right? A, B, or D, C. Okay. Now, that was relatively simple in every pattern. So the way that Squish does this, I didn't explain that, but effectively we first find ABC. And then we find ADC. And then we say, like, hey, wait a second, they look so similar, we can map them together. Let's make it considered a choice zone. And then MDL says yes or no. Maybe it says no, and then next time we find AEC, and then we try to merge them, and so on and so forth, right? But it's really per pattern. Now, these notions, like we saw in the choice zones already, so for example, edit distance Mahalanobis or edit Mahalanobis, what were the other? I mean, there were like 4 or 5, right? These are, you can use them directly as well with the word distance, but maybe there's also other uses, because together they form in a way a concept, how you can think of it, right? It's what you, if you were to have the right ontology, there would be some node that groups these and perhaps a few others together. Can we, from pure event sequence data, from the raw tokens, from the service level tokens, discover these generalized sort of ontological nodes, edit, Mahalanobis, and so on and so forth, independent, principal, and so on and so forth. And can we now find patterns over those? Such that we have, so a pattern now, for example, this is the running example in the Flock paper. Suppose we have data, the cat meows, the dog barks, the horse whinnies, something like this. Well, there is no pattern there at the surface level, but there is a pattern. It's the animal makes noise. And the moment that we, well, if somebody were to give, like, this is a set of animals, this is a set of noises, okay, then we see the pattern, right? That is what Katrin looked a bit into. But suppose we're not given this. What we showed in Flock, that we can actually discover from data which group of events is used in the same way or occurs in the same way in context of some other event, and then we can start to group them together. So we can discover on the fly a set of animals. And that's now going to be, let's say, alpha, set alpha. And we can use this in multiple patterns. We can use it in one or in multiple. We can have hierarchies over those. We can have that a group, let's say alpha is animals, right? I mean, let's say pets. And then we have farm animals, that's beta. And then we have a group gamma that combines them. Because, well, in our corpus, right, or in our data, it could be that, well, we have lots of sentences where the pets make sounds and the farm animals, they do other things, right? I mean, that's, but we also have some statements about animals in general. And for that, we use gamma. So we really go from the surface level to, can we reason, right? It's not really reasoning as you know it, right? Not logical reasoning, but can we find patterns at a conceptual level? This is where we're going. Pretty neat. Next, we can also discover Hopper. Hopper, Joscha and Paul, it was Paul's master thesis. They presented last year. Flock was 2 years ago. Hopper was last year. Hopper takes effectively Squish, or Squeeze for that matter, and it says, okay, it's cute that you allow for these gaps, right? But in a way, by explicitly penalizing these gaps with these gap codes, you basically say, I want really compact patterns. What if A happens typically 40 timestamps before B? Well, we don't even allow, that's going to be so costly to gap. We're never even going to consider it. So we can't find this pattern. That is stupid. Now, you don't want to find all possible patterns that have such long delays because it explodes in your face. You don't want that either. But we can take the idea from Omen, where we also had this delay distribution. And we saw in this one example with the Gaussian that, well, the median was 40, I think, right? And the variance was 25. We can do, can't we take this idea of a delay distribution inside a squeeze pattern? So rather than encoding after how many timestamps after A dot B happen, rather than saying gap, just say, okay, 40. And then you know exactly what you need to know. You know that it takes 40 timestamps before you can write down the B. And let's say the pattern is ABC, okay, and well, how many timestamps till C? 1, okay, good. All of a sudden, also nesting and everything becomes trivial. So it's again taking a simple problem, taking a new look at it. There we are. That's Hopper. Secret. This is, so you see that the font size is becoming rapidly unreadable. Secret is Alina's master thesis that she handed in late last year. And we're currently writing up her paper where we're finding explicitly sequential rules. So again, you can say we take inspiration from Omen, but rather than that we are given the interesting events as a separate input, we're just given one event sequence. And what we now would like to find, we see ABC, and then with a reliable delay, there's going to be DEF. That has a lot of meaning. It's very easily put, right? And you can immediately hopefully see that this is useful in many applications. But how do you do it? For that, you need an Alina. Okay, I think this is the last one that I have. No. Prosecco. Prosecco is for mining pattern-based process models. So this is literally the data from the steel factory. Can we now get a model that's essentially a flow chart where the nodes correspond to patterns? So a chunk of steel comes in and either we do ABC or we do DEF. Because, well, if we want to have particularly hard steel, it needs to go into this oven, and otherwise it goes into that oven. And it could also be, these patterns will say like, well, either oven, right? If we don't really care about the hardness, then we can, well, we just, it has to go through an oven because it doesn't need to be molten. Okay, now this one should be the final one. Consequence. Suppose that I now give you some metadata. For example, we have a customer, again, the steel factory, that says, okay, I want, well, so many chunks of steel, so flat, blah, 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 some specification, right? I mean, that's, and it needs to be done by then and such and so. Well, can we now predict what is going to be the event sequence that we will be seeing in our factory? So you could say, okay, is this even a pattern mining task? Because there's a pretty, well, yes, because we want this model to be explicitly interpretable. Because ultimately, what the goal is of process mining is like, what would happen if we would change something in the factory? What if we would add another furnace? What if we would add another rolling mill? What if we would have a call center? We hire 3, 5, or 50 more people. What is going to happen? You want to make informed decisions about that, for which you need a model that is specifiable. You can look inside what is going to happen, rather than, well, deep neural network says, yes, do it. Get 50 more people, right? I mean, maybe, maybe not. Okay. Moody. Okay, now, okay, this is the final one, because now even I here start to have trouble reading it. Moody was not a master thesis that was done a year and a half ago. And now this is truly the final one. Moody is for mining data modification rules. And there's a reason why I finished with this one, because data modification is another one of those things that I had never really thought of. And if you look in the literature, well, I'm not the only one who has never thought of this. Not do we just always assume that data is IID, which now we slowly but surely know this is stupid, and it comes with lots of risks if we do, but we also assume data to be static. Here be the data. In the real world, data is not static. So what we looked at here, the student, he, trying to think of his name. His second name is Bjarne, but it's not his, Marco Bjarne Schuster. Why I remember his second name, I have no clue. But Marco is working and was working also, everybody was at Airbus. Built large airplanes, I mean, that's very complex processes. And they noticed that, well, suppose that somebody makes an order comes in, right? I mean, that, and for that you have a certain base price. But meanwhile, like while things are going, right, well, the order gets changed, or some supplier can't deliver what, so prices change, ingredients of the airplane, of the airplane soup change all the time. That, of course, affects everything. That means the data as it was when the order was placed has nothing to do with the data at the time that we deliver the air. Which data should we now analyze? You can consider everything as a big sequence, but then what you effectively have is a very strange sequence, because the sequence are changes to the data. Effectively, update value A to 10 if such and so happens. And that is exactly the type of rules we wanted to find. That, okay, in this setup, right, I mean, if that price spikes, okay, then that is going to be the change. But the idea that data is static I mean, for me, it's now long gone. But how many methods do we have that can deal with data that is modified on the fly? As far as, well, at least one. Let me just be generous. At least one. The world is not IID. The world is not static. So I think this is the most unreadable slide, but also the most redundant slide I've ever created. But I hope this gives you a bit of an overview of all the contact points to the basics you've seen today, like all the different things that can be done. And these are the things we already did. There's at least, well, many more slides of things that we could possibly do. Good. Thank you very much for your attention. If there's any questions last minute or not, then I'm welcome to answer. Otherwise, see you again next week. Bye-bye. Bye, Max. And bye, Prakash. Prakar, sorry.